Alright. So, let's start with some vocab for matrices and some notations. Capital letters such as A, B, or C will denote a matrix, okay, as a whole. A matrix usually represent a bunch of brackets, okay, two brackets with a bunch of numbers in them. We call those elements. Okay, the numbers in a matrix are called elements. If we use the lowercase letter in brackets with I and J, it also represents, it's representing all of the elements of that matrix. Okay, the lowercase letters represent the elements. Okay, so uppercase letters represents the entire matrix. So if I have a matrix A, I would use a lowercase letter to represent any given element in that matrix. I and J represent the rows and the columns. Okay, I represents the rows. The first subscript represents the rows, and the second subscript represents the columns.
So the rows go sideways and the columns go.
Yes. Okay, so for example, A sub 3, 2 is an element of matrix A located on the third row and in the second column. Order talks about the number of rows and columns. Order is always written as a number times a number, m times. So if I had a matrix with 5 rows and 7 columns, it would be 5 by 7. Okay, 5 times 7. If a matrix has the same number of rows and columns, it's called a square matrix, but that's just a fun fact for the day. So we have matrix A listed here with all those elements. We've got 9 different elements listed in that matrix. So first we want to look at the order. Okay, again, order talks about rows and columns. How many rows do we have in that matrix?
3.
3. Rows.
So that would be a square matrix.
Yes. Rows go side to side. I have 3 rows. Okay, 3 rows. And then columns go up and down. How many columns do I have? 3 columns. So the order is 3 by 3. 3 by 3. Rows by columns, 3 by 3 matrix. Now, A sub 2, 3 is talking about the element in matrix A that is in the second row and the third column. Second row, third column. So, first row, second row. So it's going to be one of these. First column, second column, third column.
So negative 3.
Negative 3. Second row, third column. Element A sub 3, 2 is going to be in which row?
3.
Third. And which column?
2.
So what number's in the third row, second column?
Negative 2.
Negative 2.
That's not bad.
Third row, second column.
If I had to take a gander, I would say it's harder than this.
Not today, at least.
So the homework.
So, A sub 2, 3 says, what is the element that's in the second row, third column? Negative. And then A sub 3, 2 says, what is the element in the third row, second column? Computer screens are matrices. All the pixels in a computer screen, all the thousands and thousands of pictures. The computer tells it what color for each diode to light up based on a matrix. Matrices are considered equal if all the elements are the same. Okay, so we're going to say in this case that matrix A and matrix B are equivalent. So when I look at these, I have some variables in matrix A, but I have only numbers in matrix B. So in order for these to be equivalent, what does X have to equal in matrix A? 1.
Oh, it is Z would equal 3. I don't see a 1. Oh.
So what does Y have to be in order for them to be
4?
Okay. Y has to be 4 in order for 4 plus 1 to equal 5.
No, it would have to be 4.
Oops, sorry. I said 4 and then I wrote 5. Sorry. I said 4, I wrote 5. Y equals 4. 4 plus 1 is 5.
And then Z would equal 3.
They have to correspond. And then 6 equals 6. Okay? If they're equal. If they're equal, all the elements have to be the same. Alright? Matrix addition, matrix subtraction. We can only add and subtract if the element or if the order is the same for both of them. So I have a 2 by 3 or a 3 by 4 or 1 by 2. The order has to be the same for whatever I'm adding or subtracting because we add those corresponding elements in each matrix. First row, first column. First row, second column. Second row, first column. Second row, second column. However many elements we have, the corresponding row and columns get added together and then form the result at the end. So the order has to be the same. If the order is not the same, then we just say that the sum or the difference is undefined. Okay? We cannot add them if the order is not the same. Now, when we're doing our operations, I'm going to be very frank with you. Okay? Rather than Joe or Steve or anybody else. There's a lot of this that I understand you can do in your head. Point, it's not that complex. But it's very easy to make a simple mistake. If you don't make a mistake, it's not an issue. But if you don't write down some of your work, if you make a mistake, it's possible for me to help you. Because there's too much going on here. Okay, and I'm not going to spend 10 minutes staring at your paper trying to figure out where you went wrong. Actually, I'm not going to spend 10 minutes staring at your answer trying to figure out where you went wrong if you don't have any work showing me what you did. Okay? So I'm going to be a little excessive in the amount of work that I show here because that's an aid for you to understand what each process is. Okay? So I'm going to add the first row, first column of both of those. I'm going to have 0 plus negative 3. That'll give me the first element first of my matrix. Then first row, second column. What am I going to add next?
5 plus 6.
Okay. Go to the second row. 1, 8. 7 plus negative 4. Negative 6 plus 5. So all of those are getting added. Yeah. Alright? 0 plus negative 3. 4 plus 4. 5 plus 6. Negative 1 plus 8. 7 plus negative 4. Negative 6 plus 5. There's your matrix.
Finally, keep the whole thing like this.
Alright. So, what operation is this? Subtraction. So, what am I going to subtract first? Negative 7 minus negative 6. Next. 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 Okay. Be really careful with those negatives. I see those negatives disappear all the time, especially in subtraction. Be really with those negatives. Make sure that they don't disappear. Okay? Alright. Negative 7 minus negative 6. 8 minus 7. 3 minus 0. Negative 4 minus negative 5. Positive 1.
be a for real, I think we could say it's like this. Great.
Alright. This just talks about the properties of addition and how they still apply to matrices. If I'm adding matrix A to B, I can add them in either order. I'm still adding. Okay. So A plus B is same as B plus A. Commutative or associative properties, same thing. If I'm adding A, B, and C, doesn't matter the order that I add them. I can add them in any order because we still end up adding them all together. Identity. If we add a matrix to what we call a zero matrix, it doesn't change it. It leaves it alone. If I add a matrix to its inverse, I end up with a zero matrix. Okay? Add a matrix to its inverse. And a zero matrix is just a matrix that's just all zeros. Okay? Of any order, it's just all zeros. Alright? Scalar! So any matrix of order 1 by 1 that contains only one entry. Okay? So we can have a 1 by 1 matrix. To distinguish it from just a number, we refer to that number as a scalar. Scalar is multiplication. It should be scalar, either larger or smaller. Multiplied by something larger than 1. If we have a scalar larger than 1, it makes my matrix larger. And there's some applications that go with scalars. If I multiply by a number less than 1, then it makes it smaller. Okay? It's not going to change the order. The order is going to remain the same, but we're changing all the values. So if I multiply by a scalar of 5, I am literally taking every element in that matrix and making it 5 times larger. It's kind of like distributive property. Okay? I'm multiplying every element by that scalar. So, 5 times -7. Negative 35. 5 times 8. 40. 5 times 3. 5 times -4. And there's my scalar.
That's easy.
Got it.
And then what we can do is we can say, and we sometimes will be given multiple matrices, and we need to make sure we're using the correct one for whatever operation. We may or may not use it. Okay, so just because I have 2 matrices listed, or 3 or 4, doesn't mean I'm using them. Look at the formula to see which one we're going to use. So I've got -4 as my scalar, and I've got B as my matrix. -4, and then write the matrix B. And then we take everything in matrix B and multiply it by -4. Okay? Everything in matrix B gets multiplied by our scalar of -4. -4 times 3. -4 times -4. -4 times 5. -4 times -7. Notice how I'm showing that work. I'm keeping it in line. Starting with my scalar, and then I go ahead and I write that scalar inside the matrix, and then I go ahead and evaluate it. That's really important if you want help in case you make a mistake, or if you want partial credit, and to see what's going on and how you're getting those numbers. And for this one, we just ignore A. There's nothing to do with it. Extra information. Now we can combine things together. Okay, so hey, look, now I've got those 2 matrices. Now I have a different operation. I've got 2A plus. Last one didn't need A. This one needs both. So I have a scalar of 2 with -2, 5, 4, and 0, plus a scalar of 3 on 3, -4, 5, and -7. I'm going to write this underneath, okay? So if I multiply A by my scalar of 2, what does my new matrix become?
4,
8, and 0. And multiply B by my scalar of 3. Alright. Now what am I going to add? Okay. So So negative 4 plus 9. What else? 10 and negative 12. 8 and 15. 0 and negative 21. Let's see if I have enough room. I believe I can do this. Negative 4 plus 9.
5.
Yep. 10 plus negative 12. I had to like slow down so I didn't actually accidentally say the answer. 8 plus 15. And then 0 plus negative 21. What do we say? Ooh, I fit it. Look at that. Okay? So, we still follow the order of operations with scalars. Multiply before you add. Multiply before you add or subtract, whatever it is. Alright? So, yes, but we reframe it as multiplying by a fraction. Okay. We still look at scalars. We don't really talk about scalars as division. It's the same. But think of it this way. If I was taking x and dividing by 2, right? That's the same as multiplying by 1/2. And so we write the reciprocal and we change it to multiplication so that it's still, but it has the same effect. That make sense? Okay. And we're going to actually do that in just a minute. All right, so again, our properties of scalars with our properties of multiplication, okay? Some things that may make your life easier depending on the problem. All right, so remember, C and D are scalars, okay? Lowercase letters are scalars. If I'm multiplying a matrix by 2 scalars, I could either multiply the scalars and then multiply the matrix, or I could do one scalar and then the next. I'll get the same result. If I'm multiplying a matrix by a scalar of 1, it does not change the matrix. If I'm adding 2 matrices and then I'm multiplying by a scalar, I could also distribute that scalar, or vice versa. If I'm multiplying 2 matrices by the same scalar, I can factor out that scalar, do the addition first, and then the multiplication. Okay? We're actually going to do this on the next one. It's going to make our life a little bit easier doing it. All right? And then if I have 2 scalars being added and then multiplied to a matrix, I can also just multiply the matrix by each scalar and then add them. So some of those commutative, associative and distributive properties of scalars. Okay? The associative and distributive properties with our scalars. So, this is our last example today. We're going to solve for x in this matrix equation. I have 2x plus a equals b, where a is matrix 1, negative 5, 0, 2, and b is matrix negative 6, 5, 9, and 1. Before we replace a and b with the matrices, let's isolate our life infinitely easier. Isolate x first. So, if I have 2x plus a equals b, I need to do 2 things in order to get x by itself. Subtract a on both sides. 2x equals b minus a. And then what? What's the last one? Divide everything by 2. Divide by 2, by 2, by 2. So, x equals b over 2 minus a over 2. All right? So, b is being divided by 2. And a is being divided by 2. And what do we say the same thing as dividing by 2, or dividing by 2 is the same as multiplying by what? 1/2. So I can reframe this so that I have scalars as 1/2 b minus 1/2 a, multiplying by that reciprocal. So instead of dividing by 2, we're going to multiply by the reciprocal. Instead of dividing, multiply by 1/2, so that we still have that scalar. All right? And to make it even easier, I have 2 matrices being multiplied by the same scalar. Back a slide. I have two matrices being multiplied by the same scalar. I can factor that scalar out and then add the matrices first, then multiply. Since we're multiplying by a fraction, it's going to be easier to add before we multiply. Otherwise, you have to find common denominators when you're adding, and it's just a giant pain. Factor it out first. And, oops, b minus a. Factor it out first. Then we can start, now we can substitute in our matrices, do the subtraction, then do the scalar, and then we're done. Okay, so start by isolating x. That's that step 1. Okay, isolate x. This last step is optional. You can leave it like this, and that's fine. Okay? No, that's step 1. Isolate x. You could use either of these to solve for x.
Yeah. So you would just go through and subtract those two, and then divide whatever.
Multiply everything by 1/2. Okay? So, let's sub in now. What color do I want to use? Use dark red. Alright, so x is 1/2 times 1, -5, 0, and 2. That's matrix B. Minus -6, 5, 9, and 1. That's matrix A. So we're going to go ahead and do our matrix subtraction. Okay, so -1 minus what? Okay, so -1 minus -6 gives me what? 1 minus -6. Positive 7. Positive 7. All right, -5 minus what? 5 gives me. Did I write those backwards? I wrote those backwards. Jeez Louise. I'm serious. Hey, it happens to all of us, and I guarantee half of you are going to do the same thing. Okay? Yes, it absolutely matters. We're going to get totally different answers. B is 6, -6, 5, 9, 1, and then 1, -5, 0, and 2. There we go. If it's addition, it doesn't matter, but subtraction doesn't have a commutative property. Like, put it this way. What's 5 plus 2? What's 2 plus 5? That's 5 minus 2. 3. It's 5. Negative. Subtraction, the order absolutely matters. Addition, it doesn't. Addition has commutative properties. But subtraction does not. So the order matters. It was B minus A. We need to put B first and then A. So let's try that one more time now with feeling. All right. -6 minus 1. -7. There we go. I knew something was off. Felt it in my bone. 5 minus -5. Positive 10. 5 minus -5 is 5 plus 5 gives me 10. 9 minus 0. 9. And let's end with picking my color. Slow down. 1 minus 2. -1. And now we multiply everything by 1/2. Make your life easier. Leave it as a fraction. Okay? Make your life easier. Leave it as a fraction. So, what's 1/2 times -7? -7 over 2. 1/2 times 10. 1/2 times 10 is 5. 1/2 times 9. 9 over 2. 1/2 times -1. -1/2. There's my matrix. But if I had a scalar of 1/3, everything would have to be fractions because 1/3 is a repeating decimal. That makes sense? Yeah, if it terminates, you can write the decimal. That's fine. But I can do that in my head.
Okay. Yeah.
Not 7 divided by 2 takes More brain cells. I go with left brain cells. I know. So I know which things are generally easier.
Is this all that's on the homework? This is it? It's only 5.
So, here's how the next few days are going to work.